Okay, so welcome everybody. We are very happy to have Miguel again to continue his third and final lecture on the lectures on CFT analytical functional bootstrap. In case people decouple, and since this is the final lecture, I should begin by thanking Miguel for a wonderful set of lectures. They have been very educational, at least for me. Thank you very much. So can I continue, Miguel? Thank you.
Okay, yes. So this is the thanks a lot, Aninda. This is the last lecture. This is the lecture where we'll solve everything. So you haven't watched the other two, you should watch this one. So on the last lecture, so let's do a brief recap of what we learned. So this is the crossing equation for a single correlator, where you just include SL2R symmetry. So this equation holds everywhere in the crossing region, which is basically the complex plane minus two cuts that run from 1 to infinity and from 0 to minus infinity. So this is this R. And we showed basically that the constraints of this equation are completely equivalent to those arising from a set of sum rules, an infinite but countable set of sum rules involving the functional actions alpha n delta and beta n delta, where there are two. So here for alpha and beta, you can either pick the bosonic functionals or the fermionic functionals. Okay, there are two equivalent bases, and so you can go this way. So solving this implies this, and this implies these ones. Okay, so it goes both ways. And then towards the end, we showed that this is also equivalent to the vanishing of the sum rules of a different set of functionals called the master functionals. So the master functionals, they depend also on the label W or Z, whatever. It's a cross ratio, so it lives in the same region as before. Again, there are two kinds of master functionals, the bosonic or the fermionic. And so if you solve these sum rules for all W, actually, it's probably just sufficient to solve them in some open set in this region. Then this is completely equivalent to the other constraints. And finally, this is all equivalent as well to the Polyakov bootstrap, which states that the CFT correlator, which is computed here, I just expanded it in terms of conformal blocks, should be equal to the same object, but where you compute it using Polyakov blocks instead of conformal blocks. And the Polyakov blocks, they have the advantage that they are explicitly crossing symmetric. And again, the Polyakov blocks, they could be either bosonic or fermionic. And so demanding this, so all these things are different approaches to the crossing equation. We also saw that the sum rules, so when I say a sum rule, it's just, this is a sum rule. The sum rules from these functions, they apply bounds. These bounds tell us basically that on average, all solutions to the crossing equation, they look basically like generalized free fields. So we saw that there are both upper and lower bounds on the OP coefficients, that there has to be at least one operator per bin in scaling dimension space. And we also saw that functions, they can be used to study other extremal solutions in the vicinity of generalized free fields. And so you can do it in the vicinity analytically, or more generally, you can use these functions as a basis for doing numerics and probing other kinds of extremal solutions and establishing general bounds in the space of solutions. So basically, the picture I would like you to keep in mind is that there are all these connections that we should have in mind. So you have some general solution to crossing, some CFT. We saw that the solution space is a convex space, and that the corners, you have what I would call extremal solutions. So a general solution is a combination of these guys. Now, how do I know these guys? These guys, they saturate some bounds. So any CFT is constrained by these bounds, and these guys, they saturate these bounds. In turn, these bounds, they are implied by some functional constraints, and the functional constraints which imply these bounds, or the functionals that lead to these constraints, they are in a sense dual to these extremal solutions. So they allow us to bootstrap these solutions uniquely and vice versa. So if you have one of these solutions, it leads to one of these functional bases and according functional constraints. So this is the circle of ideas that we use to study this general set of solutions. So maybe I will start by getting back a bit to the master functionals, because it was maybe a bit fast last time. So there were some questions about these master functionals. So let me try to motivate them a bit better. So suppose that we've already seen how can we maximize or get a bound on a single OPE coefficient. So how would we get a bound now on linear combination of OPE coefficients? So the way that you would do that is that suppose that you find a functional omega such that its action as a function of delta, it's larger or equal than some function. I'll call this the cost function. It can be whatever you want. Usually we demand that this is 0, right? We want the function to be positive. So here it's a cost function. We can choose it to be whatever we want, positive, negative, usually to be positive. And we demand these constraints to hold everywhere above or equal to some gap. Then it's easy to see, if you have a solution to crossing, let us apply this functional to the crossing equation. So you get that 0 is equal, and now let me act with the functional. So I assume that the solution has a gap equal to delta G. So the solution looks like this, omega 0 plus this. And now I know that because of these inequalities, that this is larger than this quantity. Okay? And so from this, you learn that basically since this is positive, the sum of OPE coefficients is basically bounded by the action on the identity. Okay? Just because of this. So so this allows a bound on arbitrary linear combinations of OPE coefficients, where the combination is labeled by these C deltas. So so now so now let us just choose for this cost function. We pick it to be the conformal block evaluated at some point W, which is fixed. Okay? So we're going to demand that the functional action on delta is larger than, so my cost function will be this. The reason why this is it's a good choice is because you see that the bound that we get is that the sum over the OPE coefficients times this conformal block is smaller or equal than this functional. So I'm going to add an extra label to the functional W, because this is some parameter that I can choose, and so this omega will depend on W. And so, but now what is this? This is simply the correlator minus the identity. And so you learn that the correlator is smaller or equal than the identity minus the value of this functional at the identity.
So Miguel,
okay, so if you can find
are you choosing the cost function to be positive, or it can have both signs?
Well, here the cost function is just the conformal block, so it's positive. Right. In this case, it's positive. So if you can find a function that satisfies this, then yeah, so you get this bound. But the logic is that you want to bound linear combinations of OPE coefficients, and this is a very special linear combination, which is the correlator. The correlator is just a linear combination of OPE coefficients. So okay, so this is how you could find the bound on the CFT correlator, is by constructing a functional satisfying the right constraints. Similarly, if you want to minimize linear combinations of OPE coefficients, it's the same logic. So now you flip a sign. Again, you can choose the cost function to be the conformal block. So there's some inequality that changes, and now you find that the correlator is larger than this. Okay, so maximizing, minimizing, you just flip some signs and it works. Okay, so now let us try to get some intuition for these bounds. So what will be correlators which will optimize these bounds? So let us take a CFT correlator, and now let us expand it for small w. So when you expand it for small w, then you find that, so this is the identity contribution. And this is the contribution of the first conformal block. Okay, and then there are other terms. Well, it's a piece of the first conformal block. But what's important to keep in mind is that actually this is a pretty good approximation. You don't have to keep W very small usually. We want to get bounds only for W smaller than a half because of crossing symmetry. And so this is already quite small. So the other terms usually they're a lot smaller. And in fact, you can even improve this approximation using a different variable. But anyway, this is the basic logic. So let us use this approximation to gain some intuition. So for instance, if we want to minimize the value of the correlator, what should be the structure of the spectrum that minimizes the value of the correlator? So obviously this term we cannot touch, but here we have some leeway. So you see that W is a number that's smaller than 1. So if I want to make this very small, the OP coefficient is positive. So one way to do it is just by increasing the gap. If I make this gap very large, so I'm going to have a small number to a large power, so this is going to be very small. So we expect that the solution that will minimize the correlator, it should be very close to the solution that maximizes the gap. Of course, as you alter the gap, the OP coefficient will also change. So, you know, it's not automatic, what I'm saying, but the point is that certainly for sufficiently small W, I can always make W very, very small. And then the effect of this term will dominate over that of the OP coefficient. So certainly for very, very small W, minimizing the correlator is the same as maximizing the gap. Okay, is this logic clear? So we want to maximize the gap, but in fact, we've already seen in these lectures that there is an upper bound on the gap. The gap cannot be arbitrarily large. It has to be smaller or equal than 2 delta phi plus 1. And this bound is saturated by the generalized free fermion. And so this suggests that there is a lower bound on an arbitrary CFT correlator given by the generalized free fermion solution. And so we can now make a conjecture. Since we have a guess for what the optimal bound is, we can guess what the extremal functional is. It should be an extremal functional dual to GFF. So let us call the minimizing functional, let's add a label F. So recall for minimization, the constraints that we had to impose are these ones. Okay, my cost function is this one. I'm going to impose this for all positive delta, for all positive delta. But now, if the generalized free fermion saturates our bound, it means that these constraints, these inequalities, have to be saturated whenever delta corresponds to a scaling dimension inside the GFF solution. So when delta is equal to delta NF, so this is the dimension in the GFF spectrum, then this inequality is saturated. Okay. Furthermore, since this thing has to be positive, well, since this has to be larger than this, then it's easy to see that since the inequality is saturated here, if we don't want to violate it away from these points, then we must ask that also the derivative of this inequality is saturated at these points. So this is very similar to before we had to have double zeros. Ordinary functions, they have to have double zeros at certain points. So this is the analog. So the function which has to have double zeros is omega plus g delta. That has to have double zeros. Okay, so we want to construct a functional which satisfies these conditions 1 and 2. But we have a basis of functionals. So let's use it. Let's decompose this functional in that basis and use these constraints to fix the coefficients. And it's very easy to see then that this functional can be written as a sum of these alpha n's and the beta n's, and the coefficients have to be these numbers. So if you choose omega f to take this form, then constraints 1 and 2 are automatically satisfied. Okay. And so then this leads to this whole other story. I mean, so then I discussed various aspects of master functional last time. So now I'm going to discuss some further. But so was this clear? This logic for introducing these functionals?
Yes.
Okay. So now a very important point is that it's important to have a description of these functionals which is independent of these basis decompositions. Okay, because we don't want to work with these infinite sums usually. It's better to have just an a priori definition of what the functional is. So recall that I gave you a general ansatz for a functional in terms of some kernels f and g, right? So all the alpha functionals and beta functionals, they were determined in terms of some kernels f and g for each one. So here I'm going to call these fw and gw for this functional. Okay. Now we've already seen that a general ansatz of this form, if you relate f to g in a certain way, and if you go back to our lectures, it was basically fixing g in terms of f in this way, then if you manipulate these contours, it's possible to show that the functional action has double zeros. Okay, it gives you this sine squared, and then you get this integral. Okay, so now we don't want double zeros, right? We don't want double zeros. We want these conditions. So what should we do? Well, it's very easy. What we should do is that as our choice of g, we should take a delta function plus some g hats, and it will be g hats which satisfies this relation with f. Okay? Because if you do that, then the functional action, it will look like this. Okay, so it will be the same thing that we had before, but then there's an extra piece. This comes from the delta function. Okay. Good. So now recall that there was a gluing condition that related f and g, and this came from the fact that f and g, they arose from some other functional kernel, which I called h. And so this equation looked like this, okay, like the first line. This is the equation that we solved to find the alpha and beta functionals. But now, since I added these delta functions, there's a new contribution here on the right-hand side. And so now we have to solve this equation to find this functional. Okay? So how can we solve this equation? As I said, the homogeneous equation, the equation without these deltas, it describes these functionals. So we have to choose boundary conditions that will fix all these homogeneous solutions, right? Otherwise, I could always add one of them to this. And we want the master function to be uniquely fixed. So what we're going to do is that we will impose boundary conditions that completely rule out the possibility of having one of these solutions. So for instance, for the fermionic functionals, all the kernels, they behave basically near z equals 0, like some power of z. So we're going to demand that for the master functional, this power is softer. So it would be impossible to include any of these guys. And for the boson, it's similar. For the boson, it's almost the same thing. There's just a caveat because one of the solutions is the beta 0 functional, and the beta 0 functional does not exist, is 0, so we cannot fix it. So the boundary condition for the bosonic functional is a bit weaker than the one for the fermionic functional. Okay? Well, this one, sorry. So and we must demand also that at infinity, the functional kernels, they decay like 1 over z squared, and this was related to this swapping condition that we wanted functionals to be finite on infinite sums of crossing vectors. So we want to be able to swap the sum with the functional action.
Miguel, I have a question. Sorry.
Yes.
So for the boundary conditions near 0, for the fermionic functionals have an eta, but for the bosons, they don't have an eta. So why
Yes.
do you think like that?
Because so here it's an eta because you see the first fermionic functional that exists has a behavior z minus 2. We don't want it to appear, so we're going to demand the softer behavior z minus 2 plus some eta. So eta is just some positive number. For the boson, we cannot do the same thing because the beta 0 functional, it does not exist. But naively, if it would be there, it would be 1 over z. Okay, so 1 over z behavior is in principle allowed by this equation, and we cannot remove it by extracting a beta 0. So in general, we should allow for this behavior. And when you actually solve for the kernels, you find this behavior. So it's not inconsistent. So you demand that there is no log, because alpha 0 has a log. It's 1 over z times log. So I'm not being very rigorous here. So I'm saying there should be a power 1 over z, and there should be no log. But the 1 over z factor can be there, because there's no beta 0 functional that I could add to remove it.
Okay.
Does that make sense?
Yeah. But when you're actually fixing it, maybe you can choose for the fermions, you can choose eta equal to like integers 1 or 2 or something.
Yeah. So here, the only condition is that this should be positive.
Mm-hmm.
So it could be, it could be 1, 2.
Okay, thanks.
So, okay, then you need to solve this equation. But on the other hand, we have this representation of the master functional as an infinite sum. So basically, this is interesting because it works both ways. If you have these kernels, you can try to add them up. You can try to do this sum, and sometimes you can do this sum exactly, and you will recover this guy. And then you can test whether it satisfies this equation or not. Otherwise, if you have a way of solving this equation, then you can just expand it and read off these kernels. Okay, but of course, we have to find a way to solve this equation independently. So one way to solve it is just by an ansatz. So you just make an ansatz, and it works for special values of delta phi. So here's an example. So when delta phi is 1/2, if we pick epsilon equals -1 here, so that we are constructing the fermionic master functional. So here is an explicit expression. So this thing satisfies this equation. And the delta function terms, you see they arise because you have these poles here, z minus w. So if you work it out, if you compute this, then you get the delta function. Here naively, there are also some, but if you actually Taylor expand near these points, you find that actually it's smooth. So this is one way to solve it. The other way of solving it is by a dispersion relation. So what's the idea? So first of all, we do a little bit of a change of variables. So we pull off some square root factors from the kernel. And now we just use Cauchy's theorem. Okay. In terms of this f hat function, we just write down the Cauchy's formula. And now we deform the contour to pick up the discontinuities of f. And we know that f only has discontinuities between 0 and 1. And now the only thing that we have to do is to use the fact that it's easy to see that the imaginary part of this f hat is related to the real part of the unhatted f. But the real part of f is given here by this equation. So you recover f. Instead of getting the real part, you get something which depends only on f, and then there's some delta function. So if you work it out, then you get a kind of dispersion relation for f that looks like this. So it tells you that f is equal to this term. So this term just comes from the delta functions. And then there's an integral. It's the integral of these guys, these two terms. And there's some kernel which is given by this. Okay. So we have this expression for f. So this is not the solution, right? Because f appears on both sides. But nevertheless, this is very useful. Because this is just a Fredholm integral equation. So there are two things that you can do. First thing that you can do is that you could just solve it numerically. So you just think of this as a linear operator that acts on f. So this is just it's an equation for f. There's some matrix, and you just invert the matrix, and that gives you the solution. Okay. I mean, more explicit. So you discretize the integral, and then this is just it's a big matrix, and you invert it, and you can find f. So if you do it, so for instance, here are some of the solutions that you get. So it's very easy to do this in Mathematica. So here I'm plotting G instead of F. I've made some rescalings, but anyway. So these are basically the kernels. And I chose some value of delta phi where these special solutions are not possible. And you see that you can get, sorry, I chose several values of delta phi that start off at a quarter and go all the way to infinity. And it's very easy to get the kernels in all these cases. Okay, and you can do this for the fermion, for the boson, and it's fine. The second thing that you can do is that you can iterate this equation. So you can start off with, you say that this is your initial solution, and now you iterate. Start off with this, then you plug it into the integral, compute the integral, get a new solution, then iterate. So you can also solve it numerically like this, and it also converges fast. And it makes sense because there's actually a hidden expansion parameter here, which is the fact that this kernel, so if we go back to the expression here, you see that this kernel has this factor z prime to the minus 2 delta phi, and I'm integrating between 1 and infinity. So this means that when delta phi is large, this factor is exponentially suppressed, and so this term is also suppressed. So in particular, when delta phi is infinite, the master functional has to take this form. So this is the expressions for the master function. You see for the bosonic and the fermionic, they become the same up to a sign. And then you can compute corrections in delta phi by iterating this equation. And so indeed, you see, for instance, this is the delta phi equals infinity results. This red line is just the plot of this curve. And the numerics are clearly asymptoting to that curve. So questions on this? Okay. Right. So now let us discuss something, a very interesting outcome of this master functional approach, which is a dispersion formula for CFT correlators. So notice that I've given you two definitions of the functional action. One of the definitions was in terms of the integral of some kernels, f and g, against the crossing vector. So this is the first definition. If delta is large enough, and I will say what this means later, then you can deform the contour and arrive at a different representation that looks like this. So there's this is coming from the delta function in G, and then there's a piece which is sine squared of something times the conformal block. So here I wrote this sine squared times the conformal block as the double discontinuity of the conformal block. I will explain what this means in a bit. There are two double discontinuities, the bosonic and the fermionic, and so you get the sine squared for the boson or the fermion with the double zeros at the right places. So this is one representation, but then I also gave you this other definition of the master function as an infinite sum of these conformal blocks times functional actions, and you might recall that this is the same as the Polyakov block minus the conformal block. So if you take 1 and 2, then you find that there's a very nice representation for the Polyakov block in terms as this integral over the double discontinuity of the conformal block. Okay, so you have this interesting integral formula for the Polyakov block. And why this is interesting is because, well, for instance, this factor here is positive, because it's just sine squared times the conformal block, and conformal blocks are positive. And this kernel here, I showed you, they are positive as well, between 0 and 1. Yeah, I put the 0, so they're always positive. And so this is telling you something about the positivity properties of the Polyakov block. So this will be important in a moment. Anyway, we have this representation. Okay, before we continue, let me explain better this concept of the double discontinuity. So the double discontinuity, you should think of it as the imaginary part of a scattering amplitude. So roughly, we should think that this a CFT correlator is a bit like an S matrix. And so the connected part of the S matrix, the connected part of the scattering amplitude T is just S minus 1 divided by I. And so the imaginary part of T is the real part of S minus 1. So if we translate this thing in terms of the CFT, then the imaginary part of T is what I call the double discontinuity, and the definition of the double discontinuity is G, and then minus or plus, this depends on whether it's a boson, if it's the bosonic or fermionic double discontinuity. And then here, this is the real part of S, okay? So this is where you take Z negative. So you need to rotate Z to the negative axis, and at that point, G has a cut, and so this computes the real part along that cut. So the double discontinuity is defined as this operation. And again, it comes from analogy with this. It's the real part of S minus 1, where 1 is the Euclidean correlator and S is the analytically continued correlator. And so it's very easy to see that this definition of the double discontinuity, when you do it on conformal blocks, it gives back the conformal block times the sine squared factor. Okay. So questions about this?
Can you remind me, Miguel, did you use unitarity to conclude about the positivity, or was it
positive? What here?
Yes.
Well, unitarity, yeah, unitarity of this is basically, sorry, positivity of this follows basically from unitarity, because it imposes that delta is larger than 0, and then when delta is larger than 0, this function is definitely positive. It's sine squared times some hypergeometric function. Now, positivity of this kernel, it's not obvious at all. You have to plot it and check. I don't know what I mean. It's just it comes out this way.
But
it comes out this way, but I don't know how to prove it.
So unitarity is not delta bigger than minus a half. It is delta bigger than 0.
Delta bigger than 0.
I mean, if I put delta bigger than d minus 2 by 2 and put d equals
in d equals 1. In d equals 1. Well, if you look at the constraints, the first constraint is that delta should be positive. If you look at the norm of the first descendant, the norm is delta.
Okay.
So delta definitely has to be positive. It's just that in d larger than 1, the constraint you mentioned is always stronger.
I see. Okay.
But secretly, you have to impose the intersection of these two conditions. Delta is larger than d minus 2 over 2 and delta larger than 0. So the one that dominates is that larger than 0. Yeah, so anyway, so if you double discontinuity, it's just this part. Yes?
So the integral of the double discontinuity looks a little bit like the inversion formula. So is there any connection to that one? Or is there any?
Yeah, I think this is the I think this is the 1D version. In fact, there is an inversion formula written down in 1D by Dalemil, and so I'm going to find the dispersion relation, which I guess would be the net result of taking that inversion formula and integrating it against the conformal partial waves. It should lead to my formula, but I didn't use that.
Okay, I see. Okay, thanks.
So there is a formula for the OP density that involves the double discontinuity.
Right.
So anyway, so we have this formula for the Polyakov blocks. It has these positivity properties. This formula is valid as long as delta is large enough, right? And delta is large enough, basically, it's these two constraints. These two constraints, it just follows by looking at the structure of this kernel when you solve the functional equation. When you solve for it, you find the kernels and you find that this is only true under these conditions. Otherwise, you need to analytically continue. So the positivity properties are only guaranteed when delta is larger than this. Otherwise, this formula is not valid. Now you get something very nice. I mean, so this is the Polyakov law. But the Polyakov bootstrap tells us that the full correlator is just the sum of Polyakov blocks. So let's just use this formula for each of them and commute the sum with the integral, which you are allowed to do. And then we find the following statements. We find a dispersion relation for the CFT correlator. So it tells us that correlator is equal. There are actually two dispersion formulas, one that arises from the bosonic master functional and one that arises from the fermionic master functional. Notice that these operators are different. The bosonic double discontinuity is not the same as the fermionic discontinuity. But both of these have nice positivity properties. So these are two different dispersion relations for CFT correlators. So these bars here, these bars mean subtractions. It means that actually this is the correlator minus a few terms, and it has to do with this fact, right? Because this formula is only valid for delta sufficiently large, so you have to take the correlator and subtract a few terms such that this formula is valid. So I'm going to show this in a moment. But so is it clear? So we had this expression for the master functional action, this one, and we know that the master functional action is related to the Polyakov block, so we get this formula for the Polyakov block. And now the Polyakov bootstrap simply becomes this dispersion relation. Or there are two dispersion relations. Okay. So yeah, so this is just emphasizing. So this is yet a new way to express the constraints of crossing. So demanding that the CFT, some sum of conformal blocks is crossing symmetric, so demanding that the crossing equation holds is the same as demanding that this dispersion relation holds. Okay? So crossing is equivalent to the master functional sum rules being 0, bosonic and fermionic, and these sum rules being 0 are exactly the same as demanding that these dispersion relations are true. Okay, so this dispersion relation is equivalent to this formula. So yet another way of expressing the contents of the functional of the crossing equation. So this is just to explain, as I said, because of the fact that these kernels, these integrals will diverge if the behavior in Z, when Z goes to 0, this guy has to be sufficiently soft, otherwise this integral will diverge. And so you need to do these subtractions. So for the bosonic case, you need to subtract all Polyakov blocks up to delta equals to delta phi, and for the fermionic case, you need to subtract all of them up to 2 delta phi minus 1. Okay, so this is the definition of what these G bars are. And then this is just an equation. It's not formal, right? You can just put it in Mathematica and you can check that it's true for any CFT correlator that you like. You put it on the line, it has to satisfy this equation. It could be the 3D Ising CFT correlator, the 2D Ising, whatever. Any CFT correlator on the line has to satisfy these equations. So this immediately implies bounds. These dispersion relations automatically imply the bounds on the correlator. Why? Because I told you that this is positive and this is also positive. The double discontinuity of a correlator is positive because it's just the sum of the conformal blocks times some sine squared factors. So these integrands are definitely positive, and so you automatically learn that. So G bar with the bar upstairs is negative, and G bar with the bar lower stairs is positive. And let me see. Okay, maybe I don't. Okay, I'm not going to redo this, but these are nothing but the bounds that we've mentioned before. So this is the bound. So if we look at what G bar is, so this bound is telling us that the correlator is smaller or equal than the sum over Polyakov blocks from delta equals 0 to 2 delta phi. Okay, from delta equals 0 to 2 delta phi. So yeah, maybe I can write here. So for instance, we could have GW minus P0. And now let us put a gap. Let's put a gap all the way to 2 delta phi. Then we learn that this is negative. So if delta gap is larger than 2 delta phi. But this is the same as GW is smaller or equal than the bosonic correlator, because this guy, so P0b, is the same as GB of Z. Okay, so this bound is just an improved version of the upper bound that I wrote. It's improved because now it allows for the case where you don't impose a gap. And for the lower bound, it's a bit it works a bit differently. This is also an improved version of the bound, but in this case we don't need to make any assumptions. So this would tell you that GW, the lower bound would tell you that GW is larger or equal than GFW. So this is the same as the fermionic identity block, plus the sum over delta of A delta P delta F. Okay. So this was not the bound that we wanted, but you can show, so this is a stronger bound. It requires knowledge of the OP coefficients, but you can just plot the Polyakov blocks and you can show that this is true. So you can show that all these terms are positive. It's not trivial. It's not trivial because it does not follow from this equation. This equation cannot be used to compute these Polyakov blocks. You have to compute it using the original master functional definition, but you can just check that they are positive. And so this bound is true. Okay. So the message is that these dispersion relations, of course, the dispersion relations are a lot more general than this, but they automatically imply the bounds on correlators very simply. And furthermore, since these kernels, since the master functional kernels, they are just some superpositions of the alpha n and beta n kernels, then you can also show that starting from the dispersion relation and expanding in W, and demanding that the equation holds term by term, this reproduces precisely the functional sum rules that we already knew. Okay? So again, to emphasize, these dispersion relations really capture everything that we've done so far. They capture all the bounds and all the functional bases. They're all neatly packaged in these two formulae. So if you want, this is the apex of these lectures. So questions about these dispersion formulae?
Yeah, I have a question. So the bounds that you just mentioned for operators between dimensions between 0 and 2 delta phi minus 1. So can you obtain the same bounds using the usual Polyakov bootstrap equations somehow? I mean, can you see them?
Sorry, which bounds? The bounds on the bounds on the correlator.
The ones that you just showed on the last slide.
Well, I mean, yes. So it's just the Polyakov bootstrap. The point is just that if you don't have this expression for the Polyakov block, it's hard to prove that it's positive. If you have some other method, I mean, if you just plot them, if you just compute the Polyakov blocks using Witten exchange diagrams, blah, 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 and you just plot them and you see that they are positive, then you're good. Then you can prove the same bounds. Because, as you say, they are just a consequence of the Polyakov bootstrap. It's just that with this formula, it's automatic.
Okay.
Does that make sense?
Yeah, okay. I mean, is it?
You write the conformal, you write the correlator as the sum of these terms. And now if you know the sign of all these terms, then you can prove a bound. I
Okay.
think that's what you're saying.
Okay. Thanks.
So let us summarize what we've learned so far. So I've spoken about master functionals. We motivated them by introducing bounds on correlator values. We found that they act as generating functions for the functional basis that we've introduced. The sum rules of these functions, they encode the Polyakov bootstrap, or equivalently, they give us crossing symmetric dispersion relations for CFTs on the line when Z is equal to Z bar. And so this is a bit like an S matrix dispersion relation. So the dispersion relation gives us the correlator in terms of subtractions plus the imaginary part, right? So this is what this equation tells us. It tells us that if you know these subtractions, the low-lying terms, and you know the discontinuity of G, the imaginary part, which is double discontinuity, then you can reproduce the full correlator. In fact, this is more than an analogy. I mean, you can actually, there's a very nice link between this formula and S matrix dispersion relations in some limit, but I will not discuss it in these lectures. So questions about this story?
Yeah, I was just wondering, in higher dimensions, if you started by taking the diagonal limit of the correlator and you impose these dispersion relations, then would this allow you to get some information about these higher spin contact terms or not?
Well, I'll tell you one thing, is that if you take the dispersion relations that have been written down in the literature, they do not imply these bounds.
Okay.
So I think that's one answer to your question. So it shows that in a sense, these are not the Polyakov blocks that have been proposed so far. They are not the correct ones, I think. Because, the problem is basically that.
Sorry, you mean the two-channel dispersion relation Polyakov?
Yes.
Yeah.
Yes. 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 Yeah. So for those in the audience that don't know, so there's a version of this formula. Yeah. So there's a version of this formula, just the upper one, in higher dimensions, which involves a double integral over some kernel, and again the double discontinuity of the correlator. Okay, so it looks exactly like this. The kernels are very different. And there's also some subtractions, but really the devil is in the details, and the key is these subtractions. Because the subtraction, what's nice here in these formulas is that the subtractions are finite, right? You just need to subtract all the Polyakov blocks up to a cutoff in scaling dimensions. And usually there's just a finite number of terms that you need to subtract. If you try to repeat this story in higher dimensions with the formulae that have been written down, then this sum will involve a sum over all twists smaller than basically this, I think, or some number like this. And so actually there's an infinite number of subtractions that you need to make.
Okay.
And you can show that, yeah, you can show that for a general CFT, for instance, the upper bound, you would like to prove the upper bound that if you put a gap in scaling dimension that you get the generalized free boson. In fact, I have work with my student that we show numerically that this bound is saturated by the generalized free boson in higher dimensions. I mean, in fact, this proves it, right? I mean, this formula proves even in higher dimensions that if you impose a gap equal to 2 delta phi, then at least on the line, the bound will be saturated by generalized free boson, right? This just proves it in any dimension. But so from these dispersion relations in higher D, you cannot prove this because of these infinite subtractions. And in fact, you can look at the sign of the subtractions. It could be that the subtractions were positive, for instance, maybe they would have the right sign, such that you would still get the bound, but they don't. They have the wrong sign.
I see. And what does that imply? So you're not suggesting. I'm confused. So
it is in the Polyakov bootstrap. In this sum, there's an infinite number of terms which have a negative sign.
Okay.
So you cannot prove these bounds.
So, but you made a statement that made me feel as if the two channels symmetric Polyakov block that Mazak and Rastelli and a company have proposed, you're saying that that's wrong. That's the impression that I formed. But is that what you're saying?
I'm saying, what do you mean wrong? I'm not saying that their formulae are wrong. Their formulae are correct, but they don't have the right positivity properties. So it's just that in higher dimensions, it's sorry.
I see. No, I got it. Okay.
I'll discuss this. I'm going to start discussing higher dimensions very soon.
Okay.
But as you know, there are many choices for the Polyakov block in higher dimensions, and I don't think theirs is the correct one.
Okay.
In some sense, in the sense that you want positive sum rules.
Okay.
Maybe yours are.
Yeah. Okay. I understand the point. Thank you.
Yeah. But you could use this in higher dimensions. So this gives you some positive sum rules even in higher dimensions. So you can use this as a subset. Anyway, so now let's study some applications of this formula. Let's study an interesting application, which is to study Regi behavior. So let me just define for you, first of all, what is the Regi limits. So the Regi limit, if you take a scattering amplitude, the Regi limit is basically just the high energy limit. Okay, and there are several ways in which you can do this at fixed angle or unphysical scattering angle. But anyway, it's basically high energies. So you can define something analogous in CFTs. So again, let us take our connected amplitude in a CFT. Let me call it TZ, and I'm going to define this as GZ, the Euclidean correlator. Well, the correlator minus this transform of the correlator. And the point is that if you take Z between 0 and 1, this guy will be real, but this guy will be complex. So this is like the scattering part, and this is like the one that you subtract. This is the free part. Anyway, you just have this. I'm just defining this in this way. So why does it make sense to call this an S? Is that you can see that when Z is between 0 and 1, this correlator corresponds to a configuration of external operators that look like this. In particular, phi 1 and phi 2, they are time-like separated, and so are phi 3 and phi 4, but all others are space-like separated. Okay, 2 and 3 and 1 and 4 are, and 1 and 3, they're all space-like separated. Okay, so it's like a scattering configuration. You set up some incoming waves, and then they go out to these ones. So at this point, you might be a bit confused, because weren't we talking about 1D thing? So how come I have a 2D plot here? I mean, one way to think about that is simply that this is the same as a higher D correlator restricted to special kinematics. Okay, and those special kinematics allow for a configuration that looks like this. So it's basically forward scattering, so zero angle scattering. So I should mention that with this definition, so the imaginary part of T, what you would call the imaginary part of the scattering amplitude, it's very easy to see that it's just the double discontinuity of G. The double discontinuity is it's the double commutator. So since these guys, they are time-like separated, the correlator is necessarily complex. So, you need to tell me how to compute it on which sheet. And so the double discontinuity just takes the double commutator to give you a real number. Okay, so we have this scattering amplitude, and now we're going to study the high energy limits of this scattering amplitude. So this high energy limit, or Regi limit, corresponds then to sending Z to 1, such that we're going to do the T-channel OPE. But it's not just the T-channel OPE, because there's this term. So this term will give you something non-trivial. So in this limit, these operators, they're going to get null separated. They're going to approach these light cones, and so they will be highly boosted. So this is the motivation for studying this limit. So now I'm going to introduce some definitions. So we're going to take the limit where Z approaches 1, and I need to put some I epsilons because of this term, but so maybe you can just ignore this. And I'm just going to define, I'm going to assume that this object, when I take Z goes to 1, it's going to behave as a power law. Okay, a power law with a certain exponent and a certain coefficient. And of course, I don't know what these things are. I'm just gonna consider that a general CFT will satisfy this. And in fact, in many cases, this is true. Notice that this is the same as a different limit. It's the same as a limit where you send z to infinity. Okay, you just need to do a transform. So you just transform z to z goes to z minus 1, and these terms will swap places. This will be the 1, and this will be the s term. And so in this limit, this will behave in the same way. Okay, so I just have to do a change of variables. So sometimes the Regi limit is studied by taking this limit. What I want to emphasize, because I know some people in the audience have studied this, is that for me, it's important to have this piece here. This piece, which you might call a 1, sometimes it's a 1, but actually there are more terms hidden here, and those terms can be important. Sometimes people say that the Regi limit is just gz minus 1, but actually I think the proper way to define it is like this. Okay, and so we want to study the large z behavior of this object. And again, the large z behavior of this object is not the same as the large z behavior of this one. So questions? So like this, it's the T-channel Regi limit, and like this, it's called the U-channel Regi limit. But it's the same object. So the first thing to note is that if you just write down, if you expand the conformal the correlator in conformal blocks, then it's very easy to see what this thing is. So it's basically you get the same conformal block expansion, but now there's this factor here. Okay, so you get some oscillating piece that dresses each conformal block. And now it's very easy to see that if you look at the modulus of this object, it's smaller or equal than 2 times the conformal block, right? You just take the modulus of these two terms. And so when you take the Regi limit, we know the behavior of this guy. It's just the T-channel OP, so this is the identity contribution. And so this automatically gives you a bound. It tells you that this coefficient J0 has to be smaller than 1, and this modulus of mu has to be smaller or equal than 2. Okay, so this just follows from the OP. Now we define the Regi limit for the connected amplitude, but we can also define it for the imaginary part of the connected amplitude. So all these things, they have direct analogs in S matrix theory. So you also usually do this. And the large energy behavior of the connected amplitude is not the same as its imaginary part in general. So we're going to define the same thing for the imaginary part. And so there will be some different exponent, J bar 0. And as I said before, so whereas T is computed by this formula, the imaginary part of T, you just get the double discontinuity of G delta. So this factor, if you take its imaginary part, it becomes 2 times sine squared, blah, blah, blah. Okay, and so since this is smaller than this, you learn that J bar is smaller than J0. Okay. So for those of you who know a bit about conformal Regi theory, let me just link what I'm saying to that story. So conformal Regi theory, this is the work of Penedonish, Costa, Kornalba, and then there's also contributions by Simmons-Duffin, Kravchuk, Karen Woe, and so on. So basically, it's the statement that in a CFT, operators will lie on Regi trajectories. So it means that there's some function which is analytic in spin, and so the operators will lie along those functions. So here's an example. So the physical CFT operators are the red dots, but actually there's some analytic function that links them. Okay, so let me call those functions the Regi trajectories Ji of delta. There are many of them. Here I only drew one of them. And so conformal Regi theory, what it tells us is that the Regi limit that I've been studying is controlled by basically the intercept. So you take the first Regi trajectory and you intercept it here with this axis. So it's basically when delta is equal to d over 2. And then you call that parameter, I call it capital J0. So just to clarify the connection of what I'm saying to this parameter, you can easily show that this parameter is necessarily smaller than this one. Okay. There are works in the literature computing this for the 3D easing model, for instance. Okay, so our tool will be the dispersion relation. Okay, so the dispersion relation gives us the correlator in terms of subtractions and something which is determined by the double discontinuity. But so this tells us, it should tell us that when you look at the Regi behavior of the correlator, the Regi behavior should be determined either in terms of J bar 0, which is what controls the double discontinuity, or the subtractions. And so I won't go through the details because it's a bit technical, but then it's not hard to show. It's not too hard to show since we know this kernel, we know these kernels, we can compute the Polyakov blocks, we can study their large W behavior, and we can determine what J0 is supposed to be. And if we find that the Regi behavior, this J0 quantity, is it's the maximum of either 1 minus the gap or J bar 0. And you can also compute what mu is. You can also find bounds on various quantities that I will not discuss. So this is a simple application of the dispersion relation. So let me just develop a bit that comment that this one is important, this term here. So if we suppose that J0 is equal to J bar, so that they are both larger than 1 minus delta gaps, in that case, if we study the Regi limit in the U channel, indeed you get this 1. So that case is easy, but in general you get that this behavior would be fixed by 1 minus delta G. But so let us consider the case where it's not. So then this limit is given by this expression. It follows from the dispersion relation. And why this is interesting? This is interesting because usually this thing is studied as a diagnostic of chaos in a CFT. So if you want to find out whether a CFT is chaotic, then you consider this configuration. You have to consider something called the out-of-time order correlator. And in the current context, it just corresponds to taking Z to be 1/2 plus IT. T is the time, and then when you take the late time limit, which corresponds to this limit, you want to see whether the correlator is decaying or not. And if it's decaying, then this is a potential signal that your CFT is chaotic. So in the current context, to get decay, you see that it implies many special conditions. It implies not only that the gap, it implies a constraint on the gap, but it also implies that many of these parameters that I have introduced, they all have to be the same, and they have to be equal to 1. So to me, this seems extremely special. So it's kind of odd that chaos seems to imply such delicate conditions, but it's what follows from this formula. This is interesting because it's possible to show that this parameter J bar 0 can be related to an average of the anomalous dimension square. So if you look at the spectrum of the CFT at high energies, there will be some anomalous dimensions. There might be more or less operators, and then this J bar 0 is basically determined in terms of the average square of the anomalous dimension. And so this requires basically that the average anomalous dimension is 1. Okay, questions about this Regi limit story?
I mean, you were able to put bounds on the intercept. Is there something that you can say about the slope as well?
Bounds on the intercept. Sorry, bounds on the bounds here on J0.
Yes.
Yeah, we put them. We put bounds through this guy, but
no, I'm saying that is the slope guaranteed to be fixed to 1 or something? I mean, what is the slope of this trajectory?
the slope. Well, there's some bounds on the intercept based on the fact that this has to be a concave function.
Hmm.
Maybe that's what you're referring to.
Yeah,
So
and the slope of that line is 1, is it?
no, something like well, J. Yes, that slope is 1. Yes, you're right.
Hmm.
But this is not what I'm saying here, huh?
Mm-hmm.
Here I'm talking about the intercept.
Yeah, no, I understand. No, I was wondering whether.
But yeah, there are some bounds arising from concavity that you can prove on J0. But I mean, an important point to emphasize is that J0 does not control these limits. I mean, these are very different quantities. It's not obvious.
Mm-hmm.
So the only thing that you can show is these inequalities. In general, they will all be different.
Yeah, I was just making the analogy with S matrix theory, where I mean the slope could be anything. I mean, there is nothing sacred. There are no bounds as far as I know on the slope. I mean, it's certainly not fixed to 1.
Well, there's these well, we know that the anomalous dimensions of leading Regi trajectory has to be a concave function, right?
Yes, yes, no, that is true. Yes.
Yeah. So to summarize, so yeah, okay, I think I've said most of what's here already. So so there's an extra thing that we found is that the correlator, this dispersion relation determines the Regi behavior. Okay, so now I'm going to discuss some generalizations of this story, what I've been telling you in these lectures, and then the outlook. So first, very quickly, a couple of straightforward generalizations of what we've done. So the first one is an application to boundary CFTs. So boundary CFTs are CFTs in the presence of a boundary. The boundary preserves a subset of the conformal group. So now you have a CFT in general space-time dimension. So it lives here in the bulk, and now you cut the space in half. And then there's nothing on the other side. So here on the boundary, there's another CFT that lives in d-1 dimensions. And so in this theory, if you look at two-point functions, the two-point functions are now non-trivial functions. In a CFT, usually the two-point functions, they are trivial, right? But in the presence of the boundary, they become non-trivial functions. And this is because operators, they pick up expectation values. So when you look at the OPE of two fields, phi1 and phi2, you'll see many bulk operators appearing, and they can pick up expectation values. So this will be a non-trivial function. So this is one way to do it. The other way to do it is to take an OPE with the boundary. In this case, you expand the bulk fields in terms of boundary operators, and you get another decomposition for the two-point function. And so demanding that these two decompositions match gives you a crossing equation. Okay, so this is the bulk block expansion. This is the boundary block expansions. And they have to match. So G is not a crossing symmetric function here, the correlator. So this phi1, phi2 becomes some function G of Z. And this function has to satisfy this identity. Okay, so it's a very different setup, huh? But nevertheless, it's a crossing equation that involves a single variable. And these functions, the bulk blocks and the boundary blocks, they are actually very similar to the 1D conformal blocks. And so it turns out that for this equation, you can also study this equation in terms of functionals, and you can construct a functional basis by using the same trick. So for instance, the bulk block, you can expand it in a basis of bulk blocks and boundary blocks and their derivatives. And so from this, you can get some rules and bounds, and you can have a polyarchon bootstrap, so blah, 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 blah. So now there are three kinds of functionals. There's functionals for these guys, functionals for these guys, and functionals to these guys. So the basis decomposition looks like this. So yeah, so it's more or less straightforward generalization of what, or a different take on the work that we've done so far. The other generalization that you can consider, also relatively easy, is to bootstrap correlation functions of operators that now transform in some irreducible representation R of some group G. Okay, So in this case, when you look at the OPE of phi's, then you can split this OPE into a sum over representations. So the operators in the OPE, they are now labeled not only by the scaling dimension, but also by the representation in the group where they live in. And so in the OPE, you can only get the reps that appear in the product of capital R. And so you see that basically you're going to get a story where you just add some extra indices everywhere, the index for the representation. So the CFT correlator, now you get a bunch of them. You get one of them for each of these reps that are being exchanged. There's a crossing equation. Okay, so now since you have this index, there will be some matrix here that tells you how the representations get crossed. Okay, so this is our new crossing equation. Or if you expand the correlators in terms of conformal blocks, it becomes this. So you have a sum over states, the sum over scaling dimensions and representation. So the OP coefficients, they depend on delta and R. The crossing vector depends on R as well. So here's an explicit expression for what this is. So it's very similar to what we had before, but now it involves the crossing matrix. Before this was 1 and this was 1. Now you have these tensors. So anyway, so it's very similar to what we've done in these lectures. You just add some extra indices, and now it's possible to construct functionals that are dual to these crossing vectors. Okay, where again, you just add some extra labels that depend on this representation, and then everything follows. So it's possible to find functionals satisfying these properties, and then from these functions, you can get bounds, you can get a polyacross bootstrap, you can get a dispersion relation. So everything is the same. You just add some extra indices and you put in a bit of work, but it's possible to do it. So I should mention that this work I did with Apratim Kaviraj, and there was some work that came out at the same time by Mazza, Castelli, and Zhu. And this is work in progress with Apratim Kaviraj and Koshik Ghosh.
Hi, Miguel.
Yes.
What's the relation between the lambda 550 here and the A delta R?
Between the what, sorry?
So you have the OP coefficient and
this is lambda 550 R squared. So yeah, this is I'm missing an very important caveat here, which is that you want that these representations that are appearing here, they have to appear with unit multiplicity. So maybe this is what you're getting at.
Oh no, I was wondering, do we still have the positivity of the OP coefficient squared?
Yeah, so it's related. It's the same question. So
okay.
If the reps appear with unit multiplicity, then there's only one way to contract them when you have 4 operators, like, so you do the OP once, you do the OP twice, and then you need to contract these guys. And so these guys will appear squared. If the representations appeared with non-unit multiplicity, then there would be several ways of contracting them together, and then this would not be a square. Then you would get products of OP coefficients in different, living in the reps, but labeled by some other label.
I see.
Given by the multiplicity. So in that case, this equation would not be an equation for the squares. It would be an equation for the lambdas, and then this would be a different story. This would be more similar to doing multiple correlator bootstrap. And
right.
This I've not done.
Okay. Thanks.
Yeah. So yeah, thanks for pointing that out.
Miguel, could I ask you a question?
Yes.
Yeah. So your equation there for alpha R n at the bottom.
Yes.
So what is the argument? Is it one particular value of delta? Because I'm thinking, what if several representations contain delta of the same value? So how could you end up with this delta function RR prime?
So yeah, so this is a schematic notation. So what this means, let me know if this helps. So what this means is alpha n R acting on the crossing vector in representation R prime and conformal dimension delta. Okay, and so as you change this representation here, these crossing vectors, they are different, right? Because they are given by this expression.
I see. So the dependence on R prime is
Yeah. So if you want, I could have written I could have written this as delta M R prime. Maybe this makes it clearer. There are really two arguments.
Yeah. Okay. Thanks.
More questions? Okay. Higher dimensions, but maybe we should take a 5 minutes break.
Yeah, that sounds fine. Yeah, so
Yeah.
we'll reconvene in 5 minutes.
Okay.
Yeah, we can start, Miguel, whenever you're ready.
Yeah, can start. Okay, so now let us perhaps discuss the most important interesting generalization of all, which is to what do we do with this formulas in higher dimensions. So from some of the comments I've made, I think this is still a work in progress. I think the definitive solution has not been found yet. And I'll comment on some of the existing approaches, and then I'll discuss some work I've done in a bit more detail. So the first thing I want to point out is that indeed there are issues if you want to extend the story to higher dimensions, or more precisely to account for spin, then you run into difficulties. So now the crossing equation includes the sum over even spins. Okay, it's important that it's only even spins. And so this would suggest, let's use the same logic. Let's introduce a basis for the general crossing vector. And so since now there's spin, we're going to include a sum also over spin, okay, over j. We'll also include only even j's. And so our new basis would include not only, it would include crossing vectors with special scaling dimension and special spins. And you need to sum over all of them. And then there would be functionals which are dual to each of them. Okay, so maybe I should have written, so delta nj is 2 delta phi plus 2n plus j. And so these are the scaling dimensions which appear in the generalized free theory in higher dimensions. So the spectrum there looks like this, where j is an even integer in this 4-point function, in the 4-point function. So this is naively the first thing that you think of it. And actually, this equation, an equation that looks like this, already exists. Indeed, this is nothing but the crossing equation for crossing symmetric sums of Witten exchange diagrams. So you can define a Polyakov block, which is simply the crossing symmetric sum of Witten exchange diagrams, plus some contact terms, because these are crossing symmetric by itself. And the crossing equation for this function takes precisely this form with some coefficients that appear here. Okay, some coefficients. So it seems like we're on the right track, but actually there are problems. So one problem is that if you think of these functions, it's easy to check that the Regi behavior, so where basically it's the behavior when z and z bar go to infinity, it gets worse as you change the spin. And you recall that when we constructed the functional basis in one dimension, it was important that we knew the Regi behavior of the correlator. Because if we allowed for a different Regi behavior, the basis of functionals had to be reduced. So if the Regi behavior got worse, then we would have less functionals. In 1D, it was fine because we only needed to do this to bootstrap contact terms, and contact terms are not physical CFT correlators anyway. CFT correlators were bounded. And anyway, and the crossing you could find the crossing symmetric sum within exchange diagrams, which was Regi bounded. In this case, it seems like it's impossible. So it's very hard to imagine how you could ever find some functionals that would be able to bootstrap all the Polyakov blocks with arbitrary spins. Because it seems that you would need to ask for weaker constraints on the kernels depending on the spin. Or equivalently is that if you want to make this object Regi bounded, you need to add contact terms, but it would seem that you need to add an infinite number of contact terms. Okay, and so then it's not obvious how you should proceed in order to do this. So so this approach nevertheless has been pursued by Aninda, Papakumar, Kalol Sen, Apratim Kaviraj, and I'm sure I'm forgetting other people. Maybe Parijat was also in this. So yeah, I apologize for the names that I'm missing. So people have have pursued this, but the applications that were made were mostly in cases where these ambiguities were absent. And so one could get away with this problem. But yeah, non-perturbatively, it's not clear how to fix this, even though there's been a very recent proposal by Aninda and collaborators. Let me add another reason why you expect that this cannot work, that some new ingredient exists. If there was a basis of this kind, then this would suggest that there exist interacting solutions to crossing whose spectrum is smoothly connected to generalized free fields. Because recall that in one dimension, since we had the basis that looked like this, we could start off with the generalized free boson, and there was this flow. We went from the generalized free boson to the generalized free fermion continuously, passing along some family of interacting solutions. And the point is that along this family, you always just had one operator per bin. So the spectrum smoothly deformed from the generalized free boson to the generalized free fermion without introducing extra states. So this formula would suggest that this is also possible in higher dimensions. But this is almost for sure not true, because in higher dimensions, there's an argument that I won't repeat here, that interacting solutions to crossing require higher trace operators. So whereas the operators with these scaling dimensions, they look like this, in higher dimensions, you must also have operators with higher insertions of phi's in order for crossing to be true. So in terms of S matrices, this is the same statement that in 2 dimensions, you can have S matrices without particle production, but in higher dimensions, there always has to be particle production unless the S matrix is free. So in CFTs, there's a similar statement. So then this would suggest that we're going to need to include more terms here in our basis decomposition. Otherwise, this could never lead to those new states appearing. So there's all these reasons to think why this should be wrong. And so the solutions that have been found, basically, I mean, there aren't that many solutions, but the idea is that you have to give something up. And so basically, you can either give up full crossing symmetry, or you can give up locality. These are basically the 2 solutions that exist. So there's one approach by Matzak, Rastelli, Zhu, and also follow-up work with Simmons, Leff, and Karen Woe, where they construct the basis of this form, but they only impose crossing symmetry in the S and T channels, which implies in particular that in this basis, you need to promote this sum over spins to allow for odd spins. Okay? Where CFT correlators of identical scalars, they don't have odd spins. So here you are introducing new functionals and new basis elements. And so this is the way you get out. If you allow for this, then you can come up with Polyakov blocks. Basically, you remove this term, and then you can make something which is Regi bounded in this limit. So this is one way. Then very recently, there's been a work by Gopakumar, Sinha, and Zahed, where they propose some basis which manifests full crossing invariance. But now the basis is non-local in some way. I mean, this is still not completely understood, but it's clear that the Polyakov blocks that they write down, they also have other terms here of some undetermined nature so far. People don't understand what they are, but they correspond to some non-localities of some kind. And finally, there's a different basis that I've constructed. Well, I'm not sure if it's fair. I guess perhaps it even gives up both. It gives up crossing and localities. It seems like it's the worst possible solution, but nevertheless, this is the only case that I know that it has the right positivity properties to bootstrap an extremal solution to crossing and to get bounds. So if you want, this basis has positivity, but it looks very weird. These ones, well, this one does not have positivity. And the one that Aninda recently constructed, we don't know yet. Hopefully, this will be the best compromise between all of these. So, okay, questions about these general. This is my review of the higher D literature. It will be this. So are there more questions, or do you want me to make further comments?
I think your review was completely adequate. So it's,
Yes.
yeah, so I endorse it.
Okay. Well, so I'm 1/3 of the review. You're the other third. So there's just 1/3 missing to complain, and they're not complaining. So okay, so let's keep going. So basically now I'm gonna discuss then this somewhat weird basis that I've constructed, and why naively it just seems that it's completely crazy, but nevertheless it seems to lead to correct results. So this is a basis it has in mind applications to D equals to CFTs, although you can apply it in higher dimensions as well. I think it's a perfectly good basis in higher dimensions too, but it will not be optimal. So the starting point is the observation that if you look at a 2D CFT correlator and you look at the 2D conformal blocks, the 2D conformal blocks actually they look like products of 1D conformal blocks. So these are just the conformal blocks that we've been discussing these lectures. Okay, so it's just some hypergeometric, some 2F1. And so the 2D blocks, they have the special property, they are just given by products of these guys. And so it follows that if you write down the crossing equation in 2 dimensions, the crossing vector will take this form. So it involves some function f and some function h. So this is just the 1D crossing vector that we've discussed in these lectures. And this h is a symmetric version of the crossing vector. So h is the conformal block plus g delta 1 minus z, whereas f is with a minus sign. So the 2D crossing vector takes this factorized form. And so what this immediately suggests is that we should work with functionals that act separately in z and z bar, because we already have a good basis that will act on this factor, right? So this is the natural thing that we should perhaps pursue. And so, okay, this is very simple. So let us define some functionals, omega minus and omega plus, that include some symmetrizations. Okay, so they take a function and they symmetrize it or intersymmetrize it. So when they act here, for instance, omega minus of z will just pick up this factor, and these other factors that will involve h of z, so they will be killed. And so a general then you can take a function which is a tensor product of these guys. One factor will act in z, and another factor will act in z bar. So the tensor product of these functionals, plus and minus, acting on the 2D crossing vector, will just take, so you see there's an omega minus that acts on delta plus L. So this comes from this guy, it leads to this, and omega plus acts on this one. And then this term just swaps, it just swaps the argument. Okay, so the functional action will be this. So if you have some 1D functionals, it's very natural to take their tensor product to get functionals which act on the 2D crossing equation. Now, we already have a very good basis of functionals of this minus type, right? The alpha n and beta n functionals that we've discussed in these lectures, they act on these f's. So now we need a similarly good basis that will act on the ages. Recall that the ages are just the symmetric combination. And it will not be so surprising to you that this can be done. So you can find a basis decomposition for ages instead of f's, and you can find dual functionals to them. So let me call those functionals alpha plus and beta plus. So they satisfy the usual duality properties on GFFs. They exist in bosonic and fermionic varieties, and they give rise to a basis decomposition for these anti-crossing vectors that looks like this. So in the lectures, we've been discussing these ones, okay? The functions we've discussed so far, let's say that they are of the minus kind because they act on f's. And I'm telling you that there are some new functionals that I will not construct here, but the logic is almost identical, which now act on ages instead of acting on f's, and they will have the same properties.
Miguel, these h's should also have a spin label, or am I missing something?
Well, they have some label. So when they appear in the 2D conformal blocks, the argument is delta minus L over 2. But so this is just some parameter here. And so I'm telling you that as a function of that parameter, if you want, we could have called this h. The following is true. This equation holds. Okay? So I could have written h of z, and then alpha n plus of h, etc. And then h could have been delta minus L over 2, or delta plus L over 2, or whatever. Okay?
Okay. Okay.
So there is this basis. And so it looks like there are 4 bases of functionals that we can construct in 2 dimensions. So we take the tensor product of a minus functional times a plus functional, and now basically you can choose either boson times boson or fermion times boson, blah blah blah. So you can choose, you can make all these choices, and the basis decompositions they look crazy. So now let's take the crossing vector in 2 dimensions, and let's use these formulae. We take these formulae and we're going to plug them into here. And what comes out is this. So tau and rho are these arguments, if you want, they're h and h bar. And so a general crossing vector is written as a sum of these 2 curly f's, that the only difference is that z and z bar are swapped. And then these curly f's have an expansion that looks like this. So this is a crazy expansion, because unlike all previous cases we've seen so far, the things that we use in the basis decomposition are not of the same kind as what we are expanding. In other words, we are not expanding the crossing vector as a sum of crossing vectors. So this is not a crossing factor. So this is what I'm saying. This is not f delta L of anything for any delta NL. This is just, it is what it is. So in a sense, it's analogous to what I was saying before, that in higher dimensions, you have to give up something. You have to give up locality. So here you give up locality because the basis decomposition that you are using, it's not a basis where you're using crossing vectors themselves. You're using something else, which is close to a crossing vector, but not quite. And furthermore, you see that you have this object here, and then you have the derivatives of this object, and you also have double derivatives. So you have objects with 2 derivatives appearing in the basis decomposition. So yeah, so this seems completely crazy. So you might be disappointed. You might think, okay, so this just doesn't make any sense. Maybe mathematically it gives you something, but maybe it's not so useful. But surprisingly, this actually seems to be a good basis. So one way to see it is that there is an extremal solution to crossing, which is dual to this basis. The way to see what the solution is simply we take this formula, this decomposition, and let's plug delta equals 0 and L equals 0. So that it's the identity. And then we ask, well, I have the identity on the left. What am I going to get on the right? And at that point, magically, all these weird terms with derivatives will drop out, and the terms without derivatives, they rearrange themselves into crossing vectors. So there's some magic. And in fact, that equation becomes the crossing equation for a CFT correlator. The CFT correlator is given by this. So if you use the FF basis, it becomes the crossing equation for the correlator, which is the product of 2 generalized free fermion correlators, one in Z and one in Z bar. So this is the extremal solution that's associated to our basis. Now, funnily enough, this solution, usually it's not a physical CFT correlator. It's not a physical CFT correlator unless delta phi is an odd integer, because it's easy to check that if you take this correlator and you expand it in conformal blocks, it has an expansion, but it will include non-integer spins. So it's not physical. If delta phi is an odd integer, all the spins will become even integers, and it's a physical correlator. But the point is that even though in general this is not a physical CFT correlator because of this requirement of integer spins, the functional basis is of course always well defined. There's nothing wrong with it. It's just a bunch of functionals, so you can just use them. And furthermore, when delta phi is equal to 1, this is actually a very well-known CFT correlator. In particular, it's the 4-point function of the energy operator for the 2D Ising model. So in a sense, this basis of functions that we've constructed is adapted for bootstrapping this correlator. So this suggests that perhaps these functions, they lead to bounds which will be saturated by this correlator. So just to emphasize, the basis that functions that we found, imply that any solution to crossing in 2 dimensions implies these sum rules. Okay, so then we don't know the reverse statement. We don't know if this is a complete basis. I suspect they are, but there's something missing in the proof. You have to establish some bound on OP coefficients at fixed twists, and this I don't know how to do. But yeah, most likely this is a complete basis, but I'm not 100% sure. So what I'm saying is that we can study these sum rules, and we can study them to see whether they have nice positivity properties. And so here's an example then. So let's set delta phi equals 1 and consider the functional which is beta alpha. So it's beta minus tensored with alpha plus. So if you plot this functional, then this is the plot in the spin 0 channel. This is spin 2, spin 4, and spin 6. And so you find that the functional in the scalar channel has a negative region, and it's positive everywhere else. And then when you plot it for spin 2, you find that it starts off being positive precisely when the scaling dimension is 2. And this is the unitarity bound. So any 2D CFT, the spin 2 spectrum has to start exactly at this point. So there are no negative contributions in a unitary theory. For spin 4, it's automatic. So it's positive above 4. For spin 6, it's positive above 6. Okay. So the conclusion is that if you want to satisfy the sum rule corresponding to this functional, you see that there will be just a bunch of positive contributions, and they will have to be canceled by the negative contribution, a negative contribution which will have to live here. And so the conclusion is that when delta phi equals 1, you established a rigorous upper bound that tells you that the gap in the scalar channel has to be smaller or equal than 4. And this is optimal. It's optimal because it's precisely saturated by this correlator that I mentioned, the 2D Ising 4 epsilon correlator. Okay. So I should say that if you, in higher dimensions, if you look at other functions that have been constructed in the literature, the one that I mentioned, when you try to plot them to get a result like this, it doesn't work because they are negative. They are negative somewhere here. So they change sign somewhere here, and here they should sign around here. So this is why they don't have the good positivity properties. This is why you need to do these infinite subtractions, because there are these negative regions. These functions, they have the property that they are positive exactly where you want them to be, namely at unitarity. Furthermore, using the other sum rules, you can also prove upper bounds on the OP density, just like we did in the equals 1. You can also use the basis to do numerics and get bounds. We see that the convergence seems fast. So it really seems like it's a good basis. So for instance, the bound that you get on OP coefficients takes this form. So it's very similar to what we had before. So there's some kernel. Now it's a sine to the 4th instead of a sine squared. So this is a perfectly smooth function. It's just an envelope function. It's telling you that the average OP coefficients in a bin has to be of order of some fixed quantity, which I call the product OP density. So this quantity plays the role of the GFF OP density in D equals 1. And here it's just given by a product of OP densities for the GFF times GFF solution. Okay, so it's just some known quantities. Yeah, so okay, so because of the nice positivity properties of these functions, they also lead to these bounds. So to summarize, I told you that there are some straightforward generalizations of the functional story for BCFT and for global symmetry setups, but in higher dimensions, it requires new ingredients. There are different solutions on the market, so we discussed a couple of them. So in this work that I've done, what's surprising is that the basis seems very weird. but it seems to be the correct one, at least to bootstrap to a certain correlator. So this is a bit surprising. But it falls in line with this idea that you really need extra basis elements and some non-locality in order to proceed in higher dimensions. So questions about this?
Yeah, so I missed something. So when you constructed your 2D functionals, so in the 1D case, you chose the expansion that you did was with respect to 2 delta phi plus 2n.
Yes.
The operators that are, but here,
Yes.
what operators are you using on the right hand side?
Well, it's the operators where you see double zeros here in this plot.
I see, and this is something that is flexible.
So, for instance, for delta phi equals 1,
yeah,
it's flexible. It moves as a function of delta phi. Okay. So, in general, the spectrum will have fractional spin. So it's something like let me think. So you have to take h to be equal to. Sorry, h is equal to. Let me check I don't make a mistake. I think it's delta phi, and maybe plus 1 plus 2n.
Okay.
For the fermion case, and h bar is delta phi plus 1 plus 2n to m. Okay. I don't know why I did. And so what this means is that you get a spectrum. You get a spectrum where operators, the spacing is in steps of 4. So you see.
I see.
So this is from 6 to 10, 12 to 16, and so on. And you get quadruple zeros. So it's signed to the 4th of delta minus whatever 2 delta phi minus 2 divided by 4. So the functional actions, they contain a factor like this.
Okay. And so this gave you the optimum bound for 2D icing, but what happens if you try to, what happens in 3D? So suppose you expanded a 3D correlator like this?
I have not tested it.
Okay.
Well, I mean, so what you need to do to apply these functions in higher dimensions is that you need to decompose conformal blocks in 3D. You decompose them in terms of 2D blocks.
Right. Okay.
And so this will give you some bounds. But I haven't tested to see how constraining they would be.
Okay.
What I've done is some numerics in 2D where I use these bases, and then I can see that in some cases it converges much faster than derivatives, but I didn't push it very, very far.
I see.
So yeah, I mean, this is some basis I think it should be explored.
And is there a reason why you focus on delta phi equal to 1 as opposed to delta phi equal to 1/8?
No. I mean, you can use delta phi equals 1/8. It's just that these functionals, they are not, they will not give you optimal functionals at that point. Right. I mean, they are not dual to the spin field correlator. So right. they will give you some bound. They will give you some bound, but the bound will not be optimal.
By optimum, you mean that at the boundary, the physical theory lives at the edge.
Yes. Yeah. So these functions do not bootstrap directly the spin field correlator.
Okay.
Yeah.
I have a question. So why these this d equal to 2 functionals have this positivity property? Like, do you have a physical understanding? Like, why do they have and the other functionals don't?
Well, I mean, I think. Let me try to see. I mean, the positivity properties follow from the positivity. They follow from the positivity properties of these guys, of this guy and this guy. Since these guys are positive, it will translate in these positivity properties that you see here. I mean, this is true for delta phi equals 1. I mean, if away from delta phi equals 1, you can get negative regions. This just means that they are not optimal.
but maybe you can take some finite combination to get rid of them.
Yeah, indeed, yes.
But I guess for other proposals, like with because of this Majak and all, like they don't get.
Yeah, so in their case, it seems like you would need an infinite combinations in order to get rid of all the negative regions.
Right.
Here, no. Here it looks here a finite combination will do.
Yeah, maybe I can comment on that. So in Mazak's paper, they construct this function called phi2, which is an infinite combination. But this infinite combination is a bit of a sort of a misnomer in the sense that the reason why you need infinite number of functionals is because you're expanding on a specific point, say in my language, in a specific point in Mellin space. I mean, but a better way of doing that would be to decompose the constraint equations in terms of continuous and polynomials and get rid of the t dependence altogether.
Yes.
And so that would be like repackaging the entire set of things. I mean, getting an infinite number of summing over an infinite number of functionals if you just Taylor expanded on a specific point.
Yes. Yeah, I agree with you. Absolutely. It's just telling you that this basis that they are using is not the correct one. You need to do a change of basis, and there might be a so in Mellin space, the way to pick it out probably is something like what you're describing.
Yes.
So the other message that I would like to emphasize is that so there isn't a one size fits all. So in different circumstances, different bases will be better.
Right.
So clearly, here's an example in 2D. If you use your GF, if you ever manage to construct the Polyakov basis, a Polyakov basis with nice positivity properties, blah blah blah, and you apply it in 2 dimensions, it will not give you the optimal bound for this correlator.
Right. No, I understood, yes.
It might converge very fast, but it will not give you the optimal bound. The optimal functional is this one.
Right.
So, and I mean, even in 1D, we've seen this because we've constructed 2 bases. There's the bosonic and the fermionic one, and they have their different uses.
No, yeah, I got that point. So it's a kind of an art to.
Yes.
Yeah.
Okay, so let me finish with the outlook and some speculations. So we've been talking about the conformal bootstrap program. And so this program is to solve CFTs based only on crossing symmetry and unitarity. And so I've been trying to more or less convince you that step 1, which is to ignore spin and solving 1D CFTs, it's actually super non-trivial. And it actually captures probably a lot, if not all, of the physics that is relevant in higher dimensions, even though it's hidden and repackaged very non-trivially. Because what does it mean to solve? So solve, it means, first of all, even in the single crossing equation, which is, we've devoted almost 3 lectures to studying it, there's still lots of things that we don't understand, because we don't understand really in full the space of solutions to this equation. We don't know how to construct interacting solutions non-perturbatively. So my dream is that there will be a way of constructing them, like there's a way of constructing bases in the theory of self-adjoint extensions of differential operators. So my hope is that we'll be able to find those one day. Then we have to characterize exactly the full set of solutions in terms of these. Then once you understand this, you need to understand what happens to it when you include multiple sets, multiple crossing equations. How do they interact each other? How do you impose relative constraints between them, that you say that one operator lives in the OPE inside another one? So this is non-trivial, and it really complicates numerics. So how could we go for? I mean, imagine that in the best world, we really. So now we have very good control over the functionals, and we can we find functionals that work for systems of correlation functions. I mean, even in that case, the numerical problem could still be very hard, because you would have to understand how to put these joint constraints that operators live inside different correlators. But this is what complicates nowadays the bootstrap in higher dimensions, is because you have to do scans in parameter space to find the solution that you want. And then ideally, yeah, we also have to understand how do you find solutions to infinite sets of crossing equations. Of course, this is just a pipe dream, but this is what it would mean to solve the 1D bootstrap. And you see that we're very, very far from achieving this. The step 2 is to include spin, but again, every CFTD can be reduced to CFT1 in some limits. So it looks like if we solve step 1, we're almost done. I say almost because it's not clear to me that there could be some solutions to crossing in higher dimensions which collapse to 0 on the line. I'm not aware of any examples, but this could be true. So those solutions you would not be able to bootstrap in 1D, so you would be missing them. So maybe you don't capture everything, but it's clear that you'd capture a great deal. Of course, in practice, it's quicker to just directly solve the problem in higher D. So I'm not advocating a brute force approach of doing everything in 1D. But the message is just there's a lot to learn simply from studying this reduced problem. So that's the message that I try to convey, and that's why I said that this is a fine line. When you're on the line, you can still learn a lot. And so the outlook, I think, is that what would you like to do? So as I said, the dream of mine is that we would like to characterize these extremal analytically, or at least semi-analytically. So this would be akin to the program in 2D of finding integrable 2 to 2s matrices. I think this is the CFT analog of this. So it would be really great if the mathematical theory that fixes these functionals to have these extremal spectra could be understood. I'm sure that there's a beautiful theory waiting to be found. So, maybe some people in the audience will have achieved this. Related to this is the fact that I've written out this dispersion relations for CFT correlators. So I gave you 2 examples. I've shown you that CFT correlators can be written in a manifestly positive way in terms of a reduced set of data by using these 2 dispersion relations. So if you want, there are some theorems in complex analysis. They tell you that certain functions of Z with certain analyticity properties satisfy these dispersion relations. And you may wonder, well, what other kinds of dispersion relations could there be? Because what we expect from the functionals is that if we have an extremal solution and the set of functionals which are dual to this extremal solution, and if you look at the master functional for that solution, then you can just generalize to interacting versions of everything that we said so far. So there will be an interacting Polyakov bootstrap, and there will be an interacting dispersion relation, which will be even less trivial than the one that I've shown. And these are all some theorems in complex analysis. There are different ways of rewriting the same function in a form which manifests positivity. So it would be very nice to try to understand this a bit better. Then we should also try to understand functionals for systems of correlators. I mean, if we have to analyze every case separately, it's going to be a pain. I don't want to write 50 papers every time that I need to add a new correlation function if I need to construct new functionals. So I'm sure that there's a general structure that would apply just for an arbitrary set. So you just give me which correlators you want to find, and there will be a simple way of getting the basis that works for that system. And I'm convinced that this general structure will come through this dispersion relation picture, where we should really think of the set of correlators as a matrix which has to satisfy positive semi-definite conditions, and then we will express this matrix in terms of an integral formula which will contain the double discontinuities and some kernel, which will be a different matrix. And so our job will be to find this matrix. So I really think that this dispersion picture is the way to go for generalizations. Then for more practical matters, if you want to use these things to get bounds, to get some CFTs of interest, we need to have some efficient numeric implementation. So we need to be able to compute these functional actions efficiently, ideally as rational function approximations. We need to deal with the problem of bootstrapping systems of correlators. How do we impose these joint constraints amongst correlators? It could be that perhaps we are not thinking of this the right way. So this has been very little explored, but perhaps we should start thinking also about higher point bootstrap, because one way of avoiding to think about systems of correlators is just to bootstrap higher point functions of the same fields. And so, I mean, there's a precedent for this, is that for 2D integrable systems, If you want to solve a theory, you solve for its S matrix, and you're in the S matrix, you're always scattering the same particle or the same finite set of particles. And the way that you solve the theory is considering scattering of many, many, many particles, and you impose that all these things are consistent with each other. So this is not what we've been doing in the Bootstrap so far. We have been always scattering 4 fields, and then we just change the kinds of fields. So maybe we should also think about this other way of doing things, and maybe it will be useful. So for a higher D, I've already said a bunch of things, so I'm not going to say much, but let me just emphasize that right now we don't know what is the correct basis. I put correct between quotes because I'm not sure if there is a correct basis. In different circumstances, there could be different bases that you would like to use. But in any case, for the generalized free field basis, right now, we don't know if we have positive Polyakov blocks. So perhaps the ones of Aninda and friends will do the trick. If not, we'll have to come up with some other solution. And so if we have different bases, this suggests that there could be other dispersion relations. So there have been some dispersion relations for CFT correlators that have been written down in the literature. But if you change bases, there should be some other dispersion relations. So there should be some other theorems in complex analysis that express the correlator in terms of some data. And so again, maybe this is the correct way of thinking about it. So maybe we should think about this mathematically in a bit more detail. And so just I would like to really understand how these issues relate to this problem of particle production. How does crossing symmetry exactly imply particle production? How do we connect this with the physical interpretation of these non-localities? Yeah, I would really like to understand this. So I think that's it. Maybe just to conclude, a very important question is also what on earth are these functionals? I mean, why do they exist? Why are they positive? How can we get them by knowing the dual solution? You see that there's a link. If you know the functionals, you know the solution. And if you know the solution, you should be able to get them. So how precisely do you go from one to the other? What is exactly their physical interpretation? Because right now, they're just some mathematical tools that you can construct. But there should be a nicer physical interpretation that would explain why these things are positive, right? Because we don't know right now why they come out positive. So yeah, for me, this is a mystery, and I think it would be very important also in going forward. So that's it. Thanks a lot.
Thanks very much, Miguel. I think we should unmute and clap Miguel for a wonderful set of 3 lectures. Yeah. Questions? Can I ask a couple of questions? So this is my ignorance about the numerical aspects of the Bootstrap, and since you are the expert. When we do this 2D-izing model numerically, we see a kink at the 2D-izing model. Sorry, when we do 2D Bootstrap numerically, the original work, you see a kink at the for the 2D-izing model, but we don't see any kinks for the minimal models, right? Is that right?
For the other minimal models, yeah, you don't see.
And is it understood why there's a kink only for the 2D-izing model and not for the minimal model?
I guess no, not really. I mean, you see several minimal models that lie on a line.
Yes.
This line seems to be the optimal bound. And well, when you reach the easing model, you cannot go further because you would violate unitarity. So this line could not continue. So maybe that's one possible explanation, that the bounds will have to know about this. So at that point, the nature of the solution has to change.
Right.
But yeah, I don't know if this is a good explanation. I should say that there's another kink further up. If you keep going up, at some point it will rise, and there will be a kink at the 4 epsilon correlator, the one that I've spoken about.
I see.
This is only in 2D.
I see.
In 3D, epsilon appears in the OPE of epsilon itself, but in 2D it does not. So it's up. There's this kink. And so this functional that I constructed is a functional which sits at the kink.
And it's known in the literature, or can you point out the reference?
This kink at 4?
The second kink, yeah.
This second, I don't know the first time that it appeared in the literature.
Okay.
I've quoted it that maybe in my paper with Bernardo Zan. I think we mentioned it,
Okay, I'll have a
but I
look
think
at
it had appeared before. And I think the first person to notice was Shir al-Shuk, but it was just, you know, in some random exploration.
I see. Okay. And the second question I had was that so far as the 3D Ising model is concerned, the way that you guys had done the set up the calculations, suppose I was using your what's it called, the Julie boots, would I be able to get, say, 3 or 4 decimal place accuracy on a laptop?
For what? For 3D easing?
Yes.
Yeah.
And so why is it so in that case, why does I mean, why do you require so much computational power to and why do you require to use SDPB and things like that? What happens?
I mean, you use SDPB because usually you want to isolate some islands.
Yeah,
To get this island, you need mixed correlators, and mixed correlators you have to do it with semi-definite programming. But it's true that, you know, if you just have some criterion for, I mean, if you do a single correlator, then if you zoom in the plot, it seems like there are 2 kinks, and the 2 kinks, they approach each other. And so you could perfectly well just sit in that narrow band and read off the spectrum there. You would get less operators because you wouldn't know the operators in the OPE of epsilon itself, but you would still get very good approximations for the spectrum, for delta phi and all that.
Okay, I see.
It's a less rigorous criterion than saying that it's the island. But even on the island, you need some criterion for picking out the solution. So when you're in the island, the criterion people use is to minimize the central charge at any point on the island. This is some criterion, but there could be other ones.
Okay. Okay, and so I know that this is something that we had done for the 2D easing. To get the kink, we required only a very few number of spins. I mean, it's possible to see the kink within, I think, if you go up till spin 6 or something like that. And then in higher dimension to get, or maybe because you worked in fractional dimensions, so suppose you go systematically in fractional dimensions, does the number of spins that you need to retain to see the kink increase as you go up? Whatever, yeah.
I don't know. It's not really a question. I think that's more of an output. I mean, as you add more derivatives, you automatically get more operators, and these operators will tend out to spread in spin. So it's really, you need some minimal number of components to start seeing the kink. But in some sense, the kink is really due to a swapping between a scalar operator and a spin 2 operator. So those are really the guys that are dominating.
Yeah. No, I understand. Yes.
But to see those operators, you need to have enough derivatives, and those derivatives will increase the number of spins.
Right. Any other questions? Okay, I think we don't see any other questions. If you have any questions, I guess you can email Miguel directly.
Yes.
And thanks, Miguel, again.
Okay, thank you for this opportunity.
Bye-bye.
It's nice. Bye.